Let's go on now and figure out how many electrons and holes we've got. We can define the total number of electrons and holes as just being the integral over the density of states multiplied by the Fermi function. And so properly we should be integrating in the conduction band from the bottom of the conduction band, which is EC, up to whatever the top of the conduction band is. And you remember it doesn't go to infinity because it can only hold a finite number of electrons even when it's completely full. So this top, we don't actually know what it is, but we can make our lives simpler by recognizing that the Fermi function will go to zero anyway when the energy is very high. So it doesn't actually matter what value we put in for the top of the conduction band because there aren't going to be any electrons there anyway. So we're just going to allow this to go to infinity, and that makes our integration much more easily. Similarly, we can do the holes. We can go from the valence band, that's the top of the EV, the top of the valence band, down to the bottom of the valence band. We can say that's going to be minus infinity because 1 minus f of v is going to be 0 as we go down to these very low energies. So if we go through and do this integration, we've got expressions for g, we've got f. We can do this analytically, and we're going to get these expressions here. N is Ni, I'll define that in a moment, times some exponential which is related to the difference between the Fermi level and the intrinsic Fermi level, that's EI. This is the intrinsic Fermi level, which is the same as EF in the intrinsic material. And you recall that I said that was not exactly in the middle of the band gap if the effective masses of electrons and holes are different. But if they're the same, then it's going to be right in the middle of the band gap. Now, Ni is the intrinsic carrier concentration, Ni, and that's going to be a very important parameter, intrinsic carrier concentration. We met that already, and it's on the order of 10 to the 10 per centimeter cubed for silicon at 300 K. Now, Ni is given by this expression, Nc times an exponential of Ei minus Ec over Kt, and Nc, which is called the effective density of states in the conduction band, is given finally by this. So we can write down N in terms of Ni, which is in terms of Nc, which is in terms of all these physical parameters. We've got pi, the effective mass of the carriers, and h, Planck's constant, in there, as well as Kt. So we know what this is, this value of Nc. We know what the intrinsic position of the Fermi level is, and so we know what N is, the number of electrons in the conduction band. And we can get a very similar looking expression for the holes. It's just going to be replacing N with P. Of course, Ni and Pi are the same because this is the intrinsic carrier concentration, and so by definition we have to have the same number of holes as electrons. And instead of exponential of EF minus EI, we're going to have exponential of EI minus EF in there. So that's how we can get N and P by integrating these densities of states. We can write Ni is NV. NV is the effective density of valence band states, which has an expression similar to this, but with MP star in it instead of Mn star, multiplied by exponential of EV minus EI over Kt. So if we take the expressions we just derived for N and P, we call that N is Ni, and P has a similar expression, Ni over Kt, then we can see straight away that Np equals Ni squared. So it's the case that the number of electrons times the number of holes per unit volume is equal to Ni squared, which we know we can look this up. And for example, we've seen it's 10 to the 10 per cubic centimeter in silicon at room temperature. So this is a very useful relationship, but I should stress it's really only an equilibrium. I should put here at equilibrium. This is not always true. It's only true when the material is at equilibrium. And of course, most of the time, we're not really interested in that. If we're running a light-emitting diode or a laser or a transistor or something like that, we're not actually at equilibrium. We're pumping it, we're putting voltages across it, we're doing something with it. If it's a photodetector or a photovoltaic, we might be absorbing light and producing extra carriers. And in all of those cases, NP is not necessarily equal to Ni squared because you're not at equilibrium. So just keep that in mind. We can also write down from the foregoing expressions, Ni squared is Nc Nv. That's also true. And so therefore we expect Ni to be proportional to exp Eg over 2kT, the minus sign in there. And so this shows us that as the band gap goes up, then Ni goes down rather quickly. And this explains why, for example, gallium arsenide with its band gap of 1.4 electron volts has a much lower intrinsic carrier concentration than silicon, which has a band gap of about 1.1 eV. Let's look now at the EI. This EI is the intrinsic position of the Fermi level. That's the Fermi level in the material when there's no doping. And it's just given by mid-gap plus 3/4 kT log of the ratio of the effective masses. So you can see from here that if MP star and Mn star are the same, then this term goes to 0 and we just have the intrinsic Fermi level being in the middle of the gap, EC plus EV over 2. But as MP star and Mn star become different from each other, then we get a correction to that mid-gap state. Now, you might wonder how important this is. For silicon, we're offset from the middle of the gap by 7.3 milli electron volts. That's 7.3 milli electron volts away from mid-gap. So if we're drawing a band structure and we want to label mid-gap, and this is 1.1 eV, then we're hardly going to notice a difference from mid-gap of 7.3 milli electron volts. But there are some materials where this is actually quite a large effect. Let's look at one other thing. In a doped material, an extrinsic material, I mentioned earlier that when you have doping, and if you're dealing with a donor or an acceptor state which is close to the edge of the band, then effectively everything here is going to be ionized at room temperature. If this gap is a couple of times kT, then we're going to get complete ionization. So in a doped material, we can say that N is approximately equal to Nd, or we can say that P is approximately equal to Na, where this is the number of donors, or the doping level, per unit volume, and this is the number of acceptors. So this is the case when they are fully ionized at room temperature, or whatever temperature we're concerned with. Then we can just approximate to say that the number of donors here, the number of electrons is equal to the number of donors, and so that would imply that the number of holes, because NP is Ni squared, we can just say that the number of holes is Ni squared over Nd in an N-type material. And this is going to be a very small number, or we can say that the number of electrons is Ni squared over Na in a P-type